Hello, and yeah, first thanks for the invitation. So yes, that was it. I said, like, it's a bit of follow-up of what Michel presented this morning. So I will talk about like reinforcement learning from human feedback and like a particular variant of it, which is Nash learning from human feedback. So you may have learned about it this morning. And especially how we can use like Proximal method to solve this problem. And this is a joint work with like all those amazing people. Okay, so just for a bit of context, so basically like the training of an LLM can be split in three main stages. So first you have like the massive pre-training with next token prediction. Then you do like some supervised fine-tuning when the model will learn to follow some instruction. And finally, you have like this last part, which is like reinforcement learning, when you, for instance, if you have a task which is verifiable, where you kind of push the model on certain capabilities like math, code. And like also, if you have like preference data, you rather do like reinforcement learning from human feedback. Okay. So yes, and this like in this talk, I will only focus on the last part. Yeah. So just as a like quick reminder, so what is the difference between like this SFT phase and the and learning from human feedback or learning from preference? So in supervised fine-tuning, basically what do you have? It's like just like a prompt and a completion. And what you want to do is just learn like to generate like the completion given the prompt. So it's like a supervised training, like nothing really complicated there. The most important point is that you need like, of course, high quality data for your completion. So what you do, usually it's like you ask annotators to write them. So it's quite expensive to collect. And on the other hand, like for learning from human feedback or from preference, this time, so you have on two completion and one like preference, which say which completion is the best. And here you can afford like mid to low quality for the completions. And basically what you can do is just let a model generate them. And you only ask annotators to give like the preference label. And so it's quite clear that they are like cheap to collect, and it's kind of an interesting problem if we can leverage this kind of data. Okay, so yeah, as I said, so like the kind of data we have is like a prompt, which is basically an instruction or like a question, and like two responses. And yeah, of course, our preference sample. And basically, we are not like directly interested in the preference, but rather like in the probability distribution that will provide from which like the sample comes from. So basically, from one annotator to another, like the preference can change, but what we care at the end is only like this, like the probability that like let's say like the first response is preferred over the second one, given our context. Okay, and so as you learned this morning, maybe, so it's not completely clear how we can leverage such like data. And in particular, it's quite convenient to frame it as a game. So the game is quite simple. First, like let's say you sample a context from your data set. You have like in this game only two players, like one max player, so which generates one response, and min player that generates the other response. And like the annotator, let's say, will sample a preference. And if the max player response is picked, then the max player gets a reward of 1, min player reward of 0, and like the you inverse like the reward if the mean player response is picked. Okay. And what is nice is that once we have like formulated like this preference game, we can use like all the quantity we know in game theory to, in particular, to define what is like an optimal completion in this setting. Like, in particular, what is like an optimal policy. So I will call like a policy just like something that maps a context to a distribution over completion. So it's basically your LLM, like when you first input like the prompt and you let generate the completion. Okay, and so given like a policy for the max player and one for the min player, you can define what is called like the value of the max player in this game. So this is just, so you can see first as like the average reward of the max player in the game. And also you can see like it as like the probability that the response by the max player is picked if you average over everything, like policy of the opponent, context, and so on. And what is interesting here is that like we have naturally no like kind of an optimal policy, a well-defined optimal policy in this setting. Which is called like von Neumann winner, like in the literature. And it's basically kind of like a max-min solution to the game. So it's like the best policy you can obtain. The best policy, the policy that can maximize its value, considering that the opponent is playing optimally. Okay, and for those who are familiar with a bit with game theory, like if you take like von Neumann winner for the max player and same policy for the min player, then you have like a Nash equilibrium for this game. And yeah, it's natural to get like the same thing, like same policing on both sides because this game is symmetric. Okay. So now we have kind of a clear objective. We want to find this von Neumann winner for the preference game. But there are still something which is not completely clear, is that we know that we will not be able to learn exactly this thing. We will only get an approximation of it. And we need a way kind of like to measure how far we are from a von Neumann winner or far we are from optimality. And one way, so we can also look into game theory, and like we have like a natural quantity for that, which is called like the suboptimality gap here of a policy. So what is this quantity? It's just you take like the best value you can get when like your opponent is adversarial. So it's kind of easy to see that it's 1/2 because you can always like to fight the max player take the same policy, and like the preference will be 1/2. So that's the best you can do, and you just like take the difference between that and the value of your actual policy. And so yeah, so it's clear that this quantity is always positive, and you can see that it's like equals to 0 when you are at von Neumann winner. So when you are at optimality. So this is like the quantity we will look at for to define our objective. So we want to find like a policy that is like let's say some epsilon close to the to 0 in terms of suboptimality gap. Okay, and as you heard also maybe this morning, so like the preference game is interesting, but what we care more about is like a regularized preference game, where we have like a reference policy, so it will be basically your base model, and you will like penalize the policy from going too far from the reference model. So this is because usually you don't want your model to forget other capability when you are training on a specific one. For instance, like if you are training on summarization, you don't want to lose capability in math. And yeah, and you can redefine all the quantity I presented, but just like with this like regularization parameter to to say that you are using this regularized preference. Okay, so now what we want to do is like to learn this von Neumann winner. So how can we proceed? So we can look in like the classical algorithm for solving, like computing a Nash equilibrium in a game. And one very classic type or family of algorithm is like mirror descent. So what does it do? So first so let's say like you have like your last like policy iterate, and what you want to find is like a policy which is better than your previous policy without going too far from it. Okay, so it's quite simple. And you can show that if you apply this, you can get like some like so here it's like an approximation to a von Neumann winner at epsilon in terms of suboptimality gap, and you can get it in like a polynomial number of steps with respect to this like epsilon. Okay, so this is nice. But there is like one big constraint, is that it's only converge in on the average of the like if you average the iterates, so, and only if you average those policy here. It's not practical, of course, because you don't want to keep in memory like all these LLM checkpoint for each steps. And like the intuition behind it is that like, as if you are like kind of playing, so this is a drawing, I don't know if you can see it, like two players playing rock, paper, scissors. And it's as if you are playing against a younger version of you, so like the last iterate. And you kind of know the strategy of your past opponent, and you will just react to it. So like if it's play rocks, you will play paper and so on. And so you will have this sequence of rock, paper. So you see like you are never converging to the optimal policy, which is in this case the uniform. But you feel that if you average everything, instead of circling around, you will just like converge to it. Okay, so this is like the main drawback. And what about like, what can we do if we are in the regularized game? So like to solve this issue, we can look at even older methods, let's say, which is like this proximal point algorithm. So it's more like a conceptual methods. So it's not a practical algorithm. So it's exactly the same as before, except that now, instead of trying to improve over like an older version of yourself, you just improve over yourself. So you can see here it's not practical because like to compute, like to get the update you want, you need to know it in advance. So yeah, it's as if you are like playing against yourself. And here, like if you follow like the analogy, like you kind of feel that you will not get this like sequence things, but like you will converge faster. And actually, you have better guarantee for this thing. And like one important point to note here is that like so your update is just like the solution of a fixed point problem. So yeah, you have this big operator where you fix like the previous iterate, and if you apply it to your update, then you will get it again. So it's a solution to a fixed point. And that's interesting because you can just say, okay, but I will like approximate my update using like fixed point iteration. So I will like apply my operator again and again, like let's say capital T times. And once I did that, I said, okay, this is a good approximation of my fixed point. And I will stop there and move to the next step. So you fix just this regularization term, you apply your operator many times, and then you update your policy. Okay, and so like from a that like a recent paper of Nemirovsky, actually you only need like 2 steps. And what you get is like the Mirror Prox algorithm. And so, yes, if you look here, it's basically doing the 2 steps of fixed point iteration. And what is nice is that, so first you improve in terms of convergence rate. You move from 1 over epsilon squared to 1 over epsilon. And also you have some like, you can also get some like last iterate guarantee, meaning that it's directly this sequence of policies that will converge to the Van Neumann winner and not the average. But we still have this question about like, okay, what can we do for a regularized game? And this is kind of one of our contribution is just, okay, we will, for the regularized game, we just add like the 2 regularization term here, and that's it. We don't change anything from the Mirror Prox algorithm. And what is nice is that we keep all the same property of the Mirror Prox algorithm, meaning that so we have like a last iterate convergence, meaning that like it's these things that converge to the Van Neumann winner. We have like property in the original game also, if you tune it like a beta well here. And also very interesting point is that like in the regularized game, you have like a much faster convergence, which is like you move from something polynomial to logarithmic. So should be much faster. Okay, and yeah, I will not go too much into detail. So this is kind of like a comparison with like different algorithm in the literature. So there is this like Nash MD algorithm you may, like Michel may have presented this morning, which is kind of like in between this Nash Mirror Prox I just presented and Mirror Descent, and other algorithm like so this is a variant of DPO that you may know. Okay, and so now the question is, okay, so we have kind of like an algorithm we want to implement, or we do that. So let's try first like a kind of naive implementation of it. So we take our loss. So you can see this is like the loss that appear in the optimization problem I showed before. So yeah, let's maybe look here. Let's say it's like the parameter of your, or what we will call like the online policy. So this is like the parameters or weights of the LLM you will update. You have like the parameter of the opponent here, and some parameter of what we call like a target network. So for those who are familiar with reinforcement learning, it will make sense soon, which is like from what we will regularize here. And so the main idea is just to say, okay, I will approximate like each update, like each optimization test step we saw before, with only one step of gradient update. So it's basically what's happened here. So we just keep like the same policy for the current for the online policy and the opponent, and the target, so the reference policy here, we will update it every 2 steps, basically, like to mirror what's happening here with those 2 steps. So the issue is that this thing does not work in practice, because like doing only 1 step or 2 steps while fixing the target does not make much difference. And that's what you can see in this plot. So here like is the suboptimality gap, and here so each GPO, it's like this naive implementation of like the Mirror Prox, let's say, theoretical algorithm. And Nash MP is what I will present right after. But you can see that each GPO, it's like kind of behaving similarly as Mirror Descent. So you do not gain that much by doing 2 steps. So the idea is just to say, okay, but let's back to proximal point method. So instead of doing 2 gradients update, we will do capital T of them. So we will do kind of like a hard update of the target network every capital T update. And actually we'll prefer to do something smoother to not like waste too much time waiting for the target to be updated. We will rather do like a smooth update. So we'll do an exponential moving average here. And otherwise everything is the same. And the main point to note is that here, so there will be an implicit period of 1 over kappa for that. Okay, and yeah, last trick. Since we are using like the same policy here for like the online network and the opponent one, we have kind of like a natural baseline we can use, which is 1/2. So this is for variance reduction. And also we can, so this is like how we approximate the gradient. In our batch, like we can use like, we can exchange data from the online policy and the opponent policy to double the batch size. So these are minor improvements. And yeah, let's do some. Let's look at some experiment now. So, so first, let's try it on some like toy context or preference game, if you want. So, in this case, like the preference, so the preference probability will just be like we will sample, like the probability will be like a sigmoid of some matrix, and this matrix is just defined, so it's like sample at random from a given distribution where they have like this form, and where we control the rank here because it's like let's say it has different property according to the rank, but I will not go into details. There, like the only things we can note is that so this problem is made for like the DPO algorithm to not work well, and it's exactly the case. And if you remember, maybe this morning, like the Michal's talk, it's because of like this transitivity of preference thing. But overall, we see that so like the Nash Mirror Prox algorithm like works well, especially if you wait enough. And if we try to see like how like this soft update parameter like impacts the training, like the conclusion is that if you use like a kind of a very small soft update parameter, so for your exponential moving average, you will have like very good approximation of like the let's say theoretical update, but it will be very slow. So as you can see here with the green curve, it takes a lot of time to let's say kick up, but you will go further. Whereas if you use like a more aggressive one, you will be maybe better at the beginning, but you will get stuck because like the approximation is not good at the end of the training where you need something finer. And yeah, what's worked well, it's like just something adaptive. So you start with like a very aggressive update, and then you slow it down. Okay, and now let's look at how it works for like fine-tuning a large language model. So the pipeline is the following. So we started from like some GEMA to be only the pre-trained checkpoint. We apply first like some supervised fine-tuning to get some like a fine-tuned model, which will be at the same time our reference model and what we will use to initialize the weight of this online policy I was talking about. And then we apply like so either our algorithm or either a baseline to get the final model. And for the data, so we use like this data set, which is kind of a mix of prompts. So this is for SFT, like this first phase. mix of instruction following, math, code. And for the RLHF part, so we use kind of like a similar data set, but only with prompt. And like the preference are given by an LLM as a judge. So we also trained on some pair preference data set. And we use kind of like a bigger model for like the evaluation, because we need like more fine grain evaluation than the one we use for training. And so this is kind of like the table of our results. So how you can read it is like here. So for each column, you have like the win rate over another baseline or like models. So maybe the first thing you can note is that like all those baseline beats like the SFT checkpoint, so which is kind of like expected. And that our algorithm kind of like managed to win against all the other benchmark baseline. Sorry. Yes, and maybe this regularized safe play. It's like this mirror descent algorithm I was like talking at the beginning. Nash MD, it's kind of like in between mirror descent and our algorithm, Nash MP, and those are two variants of like the DPO algorithm. Okay, then to conclude, yeah, so we developed like an algorithm that is like grounded and that in practice kind of like provide like good result like for this like variant of enforcement learning from human feedback. But we have still like many open questions regarding this. I think like the very interesting one is like let's say for the moment we only consider one-turn data, so you have like prompt completion. What happened for multi-turn interaction? Let's say, especially if you do it for agent traces, where you have like a sequence of like tool call, observation tool call, and so on. It's not even clear how we can frame this preference game. Where do we do a preference at each round or at the end of the trace, things like that. Another interesting question is like if we have like rubric-based preference, so like preference about like the content, about the tone and things like that. How do we incorporate those different like objectives? And also an important point that I didn't mention is that so our algorithm is good, but like we have like some we have a price to pay in terms of memory, because we have to store at least like two checkpoints, so one for the online policy and one for the target network, target policy, so which could be like very expensive, and we believe there are like a way to handle this issue by maybe like doing like just like low rank approximation for the online policy, things like that. Okay, and here is like the link of the paper, and I will stop here, and thanks for your attention.
Yeah, I remember there were some results in GAN training where there was a minimax game, and the discriminator was being fooled on a small subset of images. So the generator would generate those, and then the discriminator would adapt, and then the generator would switch. So, and there was a theoretical result which I thought was similar to your rock scissor paper situation, where sort of instead of converging to the minimax thing, which if I understand correctly is the only equilibrium in theory, you get this sixtical thing. Do you have like a general intuition or a categorization of when this happens, this non-convergence, and when do you get actual or do you have to do it case by case?
So I think this happened every time you have something adversarial, like it's kind of like a risk you can have. And yeah, I believe like the main like contribution here is like the regularization part, which stabilize the training and like handle this particular issue that you observe mainly when you have like a system with like an adversarial component. And I cannot say in advance like if you have like some particular game that says this will not appear in this game, but like I think in general it's like very important.
I just wonder about practical approaches, like when you have these Nash equilibrium optimization models, like potentially this model can tell, let's say from the previous lecture example, like for Republican that the Democrats are right and vice versa, and may it impose something that cannot be moderated at all due to this nature of training.
I think if you have like some safety constraint, let's say, I think you have to add it either there like in the training. It's not clear how to do that, or you can always also like do it after, like doing one like safety training on top of this, like to be sure that this kind of behavior will not happen. But I think maybe like the next step will be more like something like about personalization, or like personalized completion, where like your example could not happen, for instance.
But then it will not be the game, the fair game, let's say.
When you have like personalized completion, you mean?
Yes, because like it will not be optimal. That's the question actually. Like we are trying to make good models and try to make predictable models. So is it possible? Because like what you do, like you use Nash equilibrium, so it will be like probabilistic and based on the like either agent's play. So may it be so unpredictable, so you cannot even in theory apply any moderation there, or like predict what it will produce.
So I would rather say that like since we do not have like, let's say, personal data or personal information, this is kind of like the best thing we can do somehow, and that's why also you will have like for sure some like probabilistic behavior, because there are some like thing unknown and you have to adapt to it, like and that's I think this is the best thing you can do given like the information you have. But I like for your specific problem, I would say like it's like to go more like for like to introduce like this personal information in the completion if you want really something like predictable and like removing this like probabilistic behavior.
Hi, thanks for the talk here.
Sorry.
I actually have a couple of questions. First of all, I was wondering, you had this nice table with SFT and sort of win rate against the couple of RL methods that you have. But I was wondering that you mentioned that for SFT you used, let's say, 2 million data, and for RL you used a different one. So I was wondering, have you had some sort of a post-training on the same data that you kind of use for RL? Because you can always change it, right? So you can turn the preference data to SFT-like in order to have the same, let's say, data sets that you trained on. Because like the win rate looks a bit sus for me. Because like, okay, I can understand the methods from below, but online DPO being that better than SFT, if you use the same data, is it like, was it used?
It's not the same data. Like we have like a separate data set for like the supervised fine tuning and another one for.
Exactly, that's the point. And this is a fair comparison then. Because like you can always turn your preference data to SFT-like one, right? To the instructions.
Yeah. So the main point was not to say we beat SFT. Like it's more to say, okay, we should at least be better than SFT doing this thing. We are not like SFT is not a baseline here.
Yes,
like
the baseline.
Are the other one. Okay. And it's like when I say okay, we have to beat SFT, it's more like a sanity check because we do something more with like with. And also with SFT, you don't have input from the the judge model we have.
Sure. There's just a lot of papers that are trying to compare SFT with RL, and that's why I was wondering. And the second one is that you said that from practical standpoint, checkpoint averaging is not something really good to have because of memory footprint. But I was wondering, is that like a real problem? Because like we do average checkpointing a lot during pre-training and stuff like that. You don't need to store every single checkpoint. You can do it on flight every time you just save it. Right?
Yeah, but this is not the same type of averaging you want. Like there are people who tried a lot, like to find ways to do to average like model, let's say policy, for this particular thing, like for solving game. And you have like several methods, and like averaging weights did not work because really it's not like the same kind of averaging than like souping weights. It's not the same thing. You really need like a uniform average over policy, and it's even more like average of like the real policy, over the whole completion space.
So for this type of checkpoint merging, you really have to store every single checkpoint.
But there are some like let's say solutions that did that. So not for these things, but more for games, where they did not store like the weights. They store like some action, let's say, and they have kind of a replay buffer where there's sample from it uniformly, and you have like some nice tricks you can apply. But like this kind of algorithm works like as well, let's say, and they are kind of simpler to implement.
Thank you so much.
Any more questions? Okay, let's thank Pierre again.
Thank you.